So my name is Joerg Polzehl. I am a researcher at the Weierstraß-Institut in Berlin. And what I plan to do today is give a slightly different view on image denoising with quite a lot of applications to what you probably know from total variation, regularization, and numerical methods. So this talk will be about a statistical approach that we have been working on in Berlin, let's say for the past 15 years. So I will start with some words about a general idea that we developed together with Vladimir Spokojny in the beginning of the 2000s. And then I will explain the basic approach, give some information about theoretical properties of the approach, then show some generalizations, examples in 2D, 3D, and the second part will be devoted to applications in MR, where we try to use these methods in diffusion MR and quantitative MR imaging. So let's start with the observation that we had about 15 years ago. And that's, if you look at images, many of these images are characterized by regions of local homogeneity and discontinuities between these regions. So that's true for, let's say, the satellite SRR image that you see here. That's true as well for an MR image where image intensity corresponds to certain tissue types. It's true for CT and partly true even for natural images like this parrot here. So the problems that we were thinking about in the beginning were using assumptions of local constant or local smooth images, and then to use this assumption in order to improve on edge detection and use it for image denoising and image segmentation. And another class of problems that we were looking at were local stationary time series, where you often have similar situations that for a certain time a process follows a certain regime, then you have a change in regime, and then again it continues local as a local stationary process for some time. Okay, starting point. So images that we are now looking at are, for instance, images in functional MR, where we try to improve signal detection in FMRE, especially improve on the description of activated regions. Then what you see here on the left side is color-coded FA map from diffusion tensor imaging, quite noisy. So the idea is to use smoothing methods in order to get a clearer image about fiber orientations and regions in 3D where fiber orientation is homogeneous. All on the right-hand side maps from quantitative MR. So what we have here is a so-called R1 map, a proton density map, and R2 star map. These images are quite noisy because here the aim is in high resolution MR, looking at detailed structure, and high resolution MR comes with a drop in SNR. The general idea. The structure of these problems is quite common. You have a design X in some p-dimensional space. Often observations are on a grid in case of images. You have observed gray values or color values or vectors of characteristics. And these observations follow a certain probability distribution. So probability distribution P, which is parameterized by some parameter theta depending on location. And there's interest in a mapping of theta from the design space to the parameter space. So in principle, that's something like a regression problem that you try to solve here. Usually, you assume that this mapping of theta is characterized by local homogeneity, and between local homogeneous regions you have discontinuities. So we start with a qualitative structural assumption, and this qualitative structural assumption is that we assume that there exists a partitioning of the design space into regions xm such that the parameter is constant within regions, and that we also allow that some components of theta may be global parameters here. So the general idea is to determine the structure, so the local homogeneity regions, and the parameter values of theta by inspecting scale space. At each scale, we define a local model by a weighting scheme. So x is the design point. W1 to Wn of x are weights assigned to all other design points. And then, so this describes homogeneity structure in the sense that some of these weights can be 0, some of these weights can be 1, or in intermediate stages of the procedure, some of the weights can be interpreted as confidence for a certain design point to belong to a certain homogeneity region. And then we use information on the structure that we gain on small scales to determine weights on larger scales. So the algorithm, in principle, or all these algorithms have 4 steps. One is initialization, and usually they are initialized by the observed values. So small scale, local neighborhoods containing only the observation itself. Then what we do is we try to learn about the parameter from information on the partitioning that we get in weights. we learn about partitioning by comparing estimates from former steps, and we iterate inspecting scale space from local to global. Let's be a little bit more formal. So we characterize structure by weighting schemes. So at each point in the design, point I or xi, we have a weighting scheme wi in step k. These weights, they are computed as combining two types of information. One type of information is locality in or distance in design space, and this is done using kernel function k location, and it depends on a on a distance or metric in design space and on a bandwidth hk. And the second part is a kernel that acts in intensity space. And what we use here is a Colbert-Leiber distance between probability distributions with estimated parameters. And additionally, there's a factor ni, k minus 1. And this is the sum of weights used in order to get an estimate theta hat I in the preceding step. And this somehow mimics variability of the estimates. Estimation itself is done using weighted likelihood, or in the Gaussian case, weighted least squares. Okay, so this leads to an algorithm which depends on prerequisites, metric in RD, Colbert-Leiber divergence in order to measure difference between probability distributions with different parameters. Kernels, for the kernels we assume that they are defined on a positive axis. They are monotone, non-increasing. Their value at 0 should be 1. The integral over the squared kernel should be finite. And it is an advantage here if the kernels have compact support. And then we consider a sequence of bandwidth 0, 1 to H0 to HK star, such that going from one bandwidth to the next, the variance reduction for a non-adaptive procedure, so a procedure where only the location weights are employed, decreases by a factor CH. The algorithm starts with initialization, then adaptation, defining weights, estimation, getting estimates in all design points, and this is iterated, increasing the bandwidth from step to step until a final number of steps or predefined defined number of steps is reached. Okay, just a short illustration. Here we have observations of a univariate regression function, local constant. The estimates that we get.
May I just ask a question?
Yes.
So you have this condition of the Colbert-Leiber divergence. Can you motivate this a bit more? Because you plug in on one hand side the image, which is the theta, and on the other hand side the probability distribution, and you expect that the outcome is the same if you understand correctly.
In principle, what you use the Colbert-Leiber distance here only to measure distances in image space, in the intensity. And so in the Gaussian case, this simply would be the least square would be a quadratic distance scaled by the variance.
Okay.
For other distributions, you get a slightly, you can use this as an approximation, but usually for other distributions, the Colbert-Leiber distance between distributions, given the parameters, is a little bit larger. And Colbert-Leiber distance here is used in order to have a natural extension to exponential families.
It's just this equivalence wasn't so immediately clear to me, so that you have the image of the thetas and theta primes on one hand side, and the p theta and p theta primes on the other side. So what you seem to motivate is the p theta side.
Yes.
And why does it need to be equal? So what's the rationale behind? So maybe I go the second bullet here.
Yes. So here at this point, what you get in the procedure is relaxation in locality. From step to step, you are increasing the bandwidth. And on the other side, if you are inside homogeneous regions, then your weighting scheme is extending. So this Ni, sum of weights, is growing. And this Sij inside homogeneous regions is something like 0 plus a random part. If you have two different regions, you're in the situation that there is a difference in parameter values. So what you get as Sij is this difference in parameter values measured by Colbert-Leiber distance plus some random part. This gives you separation on one hand, and also, if it's designed correctly, gives you expansion inside homogeneous regions.
But it's kind of two different steps, so it's not like one integrated procedure. So you have one way to determine the weights, which is motivated here, then you have the second step, which is solving the optimization problem for getting into image.
Yes.
Yes, okay.
And so what's going on? Here, increasing the bandwidth, you somehow adapt to the function. And if you look at the weighting schemes, the first row shows the location weights for different bandwidths. And the location weights, they are getting less and less informative. And on the other side, information about differences between parameters, here differences about the value of the regression function, is accumulated in a statistical penalty, that's this Sij. And what you have here is, in the beginning, you have a situation where you clearly see that there is a difference between the second interval and the second and the third interval, and the differences between the other intervals are not that clear. And if you increase the bandwidth, if you go up in the sequence of bandwidths, then what you end up with is a clear segmentation that shows up in the statistical penalty. So this is accumulating information about separation. And if you combine the weights, then what you end up is clearly segmentation of the design into 4 homogeneous regions here.
I mean, if I will translate this into some variational approach, the Ks would be something like the data fidelity, in a way, and the k log would be some local weight, which could be some quadrature rule or whatever. So this is how it looks.
I think it would be somehow like the first step constructs some weights, then a weight to be so, and the second step would then solve with these weights.
Yeah.
This is my impression.
Yeah, but I was just looking at the weights because somewhere there is an implicit fidelity perhaps. This is the Sij, which measures the difference between intensity values, which could be, for instance, some image residual.
Just to be sure, the number of regions does not need to be fixed, right? The number of regions can be completely arbitrary. It doesn't need to be
It can be completely arbitrary. The form of the region is completely arbitrary. The idea is to recover both the form of the regions and the value of the function inside the regions.
But the k log, maybe I look at it from a different angle, but the k log is fixed, so this determines your localized averaging. So what does it mean to determine the? Okay, so in the image region, so the piecewise constant regions, for instance, they are not fixed; they're determined automatically. But the way how you localize the SIs is fixed.
The way you localize is the same as in conventional kernel smoothing, or if you use a Gaussian kernel, it would correspond to isotropic diffusion.
But would you allow different, let's say, neighborhood radii in one stage, or are they all degree? Okay.
So there are potential neighborhoods, which are determined by the location kernel, and then you have actual neighborhoods or actual weighting schemes, which also incorporate the information coming from comparing estimates. Okay, parameters. One parameter is k star, which determines the maximum bandwidth, number of steps in the algorithm. This, in principle, can be chosen looking at variability reduction that I want to get, and also it determines the numerical complexity of the algorithm. So how much time do I want to spend? And third, if the structure assumption is not valid, so if I have a smooth behavior of the parameter inside homogeneous regions instead of a constant, then also the maximum bandwidth should somehow correspond to a bandwidth which is optimal in handling the smooth part inside the regions.
So if I would, in this piecewise constant example before, if I would continue and let k go even further, what would happen? Would it become stationary, or would it?
It stabilizes.
Stabilizes it.
It completely stabilizes if the discontinuities are large enough, and if I have complete homogeneity in the sense of constant parameters inside the region.
So like in this case, it would stabilize at this solution that you have.
Yes.
So which means in principle you could write down a stopping rule. Because adjusting the number of iterations by max is always a matter of choice, but you could write down a condition so that you automatically determine a useful case star.
Yes, one can do this using ideas that are, for instance, in the pointwise adaptive procedures that Weierstraß-Institut is using inside homogeneous regions. Okay, the second parameter is this decrease in variance by a factor CH. And what we use here is 1.25 to the power of 1 over dimension. So in a three-dimensional case, it would be 1.25 variance decrease, which results in a decrease in bandwidth, in an increase in bandwidth by 1.25 or 1 over dimension. Okay, and the default kernels that we use are the two that you see here. Both have compact support, easy to compute, and the second one has a so-called plateau in the first half. So it's constant 1, and then it decreases to 0 linearly. The interesting point is, or interesting parameter is the parameter lambda, which is, let's see, which we have as a scale parameter here. As a scale parameter for this Sij. And this parameter can be chosen by a so-called propagation condition. And this propagation condition in the kern form that we use was formulated by Saskia Becker in her PhD thesis 2014, and reads that if you compare in a completely homogeneous situation, so constant parameter over the whole image, the non-adaptive estimate to the adaptive estimate. The difference should be restricted in the following form. So you say a function, you define a function set depending on the parameter lambda that you are interested in, step k and the probability p as the infimum of set larger than 0, such that the probability that the penalty, so covert-Leiber distance between the adaptive estimate and the true parameter, times the sum of weights of the non-adaptive procedure, so only using the location weights, is smaller than p. This function should be non-increasing for all p exceeding p0 as a function of k. The interesting point is that this parameter lambda can be chosen by simulation in a non-informative situation, and therefore does not depend on the actual parameter. It depends on the size of the design, let's say on the dimension of the problem. So it differs whether it's a 1D, 2D, 3D, or other problem. And it also depends on the probability distribution. So the value of lambda is smallest for Gaussian distributions and is slightly larger for other exponential distributions or exponential classes. Visualization of this on the left-hand side, what you have is the covert-Leiber distance between the parameter, estimated parameter using the adaptive procedure, the parameter theta, true parameter in the simulation. Alpha is some factor by which this exceeds the covert-Leiber distance between the non-parametric, non-adaptive estimate and the true parameter. This is plotted as a function of alpha and k. And on the right-hand side, you have the inverse function of set lambda as a function of p. And so what you expect to see for a reasonable lambda is that these lines that you see here, you have the probabilities plotted here in the lines, that these are parallel, and that you see this non-increasing property. So lambda, the choice of lambda in principle depends on how much deviation you would like to allow between the adaptive and the non-adaptive estimate in a homogeneous situation. Okay.
But what was lambda again?
Lambda is the scale parameter for the statistical penalty. So it's type of regularization parameter that does not depend on the data itself. It only depends on the distribution and slightly depends on the design. Okay, theoretical properties. Under homogeneity, you get that the probability of the statistical penalty exceeding a certain value set can be bounded by 2 times e to the power of minus. Under local homogeneity, you get a similar result for interior points for the local homogeneous region. And then there's a separation property that says that there exists a set larger than 0 such that the weights for point J when calculating the estimate at point E is 0 if the Kullback-Leibler distance times Ni, so the sum of weights from the previous step, exceeds some value theta ik, and the theta ik should be larger than this quantity here, where this kappa squared depends on the probability distribution. Okay, extensions. So for color images, you have a local constant model, you have linear variance mean dependence, you have correlation between channels, and you have some spatial correlation. This can be incorporated here. And what we get is, this was so this is a noisy image, this is the reconstruction, maximum bandwidth 8, and what you see in the sum of weights is the discontinuity structure. So there where you have discontinuity, the growth of the region and growth of sum of weights is restricted, and it shows up as smaller values of sum of weights. Okay.
Do you know the type or the intensity or the strength of the noise before you apply your package?
What we do here is we assume that the noise level is homogeneous in the image, and then we simply estimate it using some robust estimate which filters out the effect of discontinuities. And so for locally smooth images, there are 2 generalizations. One would be to assume a local polynomial model. So a local polynomial in some orthogonal basis psi. What we need then is a parameter translation. So this is centered in design point xi. We need a parameter translation between models centered in j and centered in I, and then we get a penalty like this here. And the initial bandwidth is determined by the order of the polynomial system, and what we get is a local constant parameterization. So the assumption here, structural assumption is that the image can be described local polynomially with constant parameters inside the homogeneous regions. And there is a second approach that I'm currently working on, and that's using patches. So you consider local vicinities, patches of a certain size S, and then the penalty that you're using is the maximum over all penalties that you get for point pairs inside the patches. So the idea here is similar to non-local means, except that this defines the local means procedure. Okay, examples. We have seen this in different talks, so I just tried to use it here. The original image, noisy image reconstructions by the adaptive weights smoothing procedure, that's what I've explained as structural adaptation. The local polynomial, order 1, bandwidth 6, patch-based version of the method, non-local means, total variation with optimized parameters using code from VS, and the structural adaptive procedure with optimal choice of bandwidth, maximal bandwidth. If I increase the noise level by a factor of 2, what we see is that still non-local means and slightly better our patch-based method with best results. If I increase it again by a factor of 2 and again by a factor of 2, you see that in principle it's you get slightly better results by the patch-based adaptive weights procedure compared to non-local means or total variation regularization. What you see for the original adaptive weights in all these images is that somehow they tend to go to a local constant approximation if the bandwidth is increasing. So there the local constant approximation is enforced.
So just a quick question. So the TV opt is the one with local regularization, or so it has a distributed regularization weight?
These are calculations that Carsten did with code from Carlos Rautenberg.
Okay, so that's localized.
So everyone compare with the BM3D. Did you try that one?
Yeah. No, I didn't. Okay. So if you go to 3D, what I want to emphasize on is how oversteps for the adaptive weights, the patch-based adaptive weights with 3x3x3 patches and 5x5x5 patches, how this behaves in terms of peak SNR over steps. And what you see is that again increasing the noise level, what you see is that somehow adaptive weights enforces local homogeneity in the sense of local constant reconstruction, while the patch-based methods even at high noise levels and even going to larger bandwidths. I had to stop at a certain point because of computational time. Recover most of the structure in the original brain web template. Okay, so even here at this level. Okay, what we are really interested in the moment is in vivo brain histology using MR. And here, what we aim for is anatomical microstructure, and then look at population variability, inter-subject anatomical differences, investigation of rare diseases. This all requires high image resolution, and in case of diffusion MR also requires multiple high B values, and both lead to very bad SNR in image. Statistical problems that we face are related to statistical properties of MR data. I will explain it in a minute. To extremely low signal-to-noise ratio, and to consequences of both these complications for statistical modeling. Modalities that we are currently looking at are diffusion MR and multi-parameter mapping. Okay, that's explanation of the data. So data acquisition in MR is done in k-space, and k-space information is translated into image space by a fast Fourier transform. These recordings are done on a multi-coil, usually 24-32 coil system. And the information from the multiple coils is then combined using techniques like Grappa or Sense to a combined image in image space. This has consequences, or the method used here has consequences for the distribution of the data. So the signal standardized by the noise level in k-space or in image space for the is distributed non-central shy with number of degrees of freedom equal to 2 L star. L star is something we call efficient number of receiver coils, which is, depending on the method, between 1 and the actual number of receiver coils. And theta divided, standardized by sigma, is the expected, is the theoretical signal in a noise-free situation. Signal distribution depends on the reconstruction method. It's Bayesian for if information is combined in a complex space. It's approximately non-central. If coil-specific magnitude images are combined by sum of squares. Parameters L star in sigma may depend on location, and the acquisition protocol and reconstruction method causes usually spatial correlation, which is another complication here. So that's again signal distribution. So you have an first moments depending on the noise-free signal sigma I that we want to use in modeling, and variance also depending on the variance on the scale parameter sigma and on the number of coils. What you see is, if you look at the densities for different non-centrality parameters, what you see here is that there is a gap between expected signal and theoretical signal. And this gap is something that has to be handled in modeling, and usually is currently not. Okay, diffusion weighted imaging. What you have here is a situation where additionally to recording MR images, you are also recording MR images when additional magnetic field gradient is applied, which causes water protons to move and move back. And what you are trying to model is the amount of water molecules that has changed position due to diffusion. Usually that's done with different gradient strengths, which corresponds to different B values. And what you have is in each voxel you have a set, green, red, blue of measurements on in different directions for different gradient strengths. So what you measure is water diffusion. So that's directional information, and the simplest model to use here is the diffusion tensor model, which relates the basic image intensity, the B value, the gradient direction to the observed signal, or to the theoretical signal, better to say, by description of the diffusion tensor, DI. And this is then used in order to get something like color-coded FA map here. Color corresponds to direction, and intensity corresponds to anisotropy of the tensor. And based on the vector field given by the mean, by the first eigenvectors of the diffusion tensor, what you usually try to, or what you may try to construct is a reconstruction of the wire length of the brain in the sense of fibers. Okay. One problem that immediately comes up if you want to deal with bias or if you want to smooth this type of data is accessing variability. And so you need noise variability for adaptation, you need it for description of bias, and this information is not easily available. Assumptions that we make is that we have a local homogeneous signal corresponding to different tissue types and orientations, and that we have spatially smooth sigma. And then we can design a structural adaptation algorithm which has one additional step. It employs smoothness of sigma by median smoothing, local median smoothing. And otherwise it coincides more or less with the standard algorithm. Okay. This is what we get for high resolution DMI data set from Leipzig. First one is B0 value, second one are diffusion weighted images. So there are replications in this. On the right hand side, what you see is the relative error in estimation of sigma obtained from so these are estimates of sigma, and this is the relative error obtained from replications. Okay, next problem. We have analyzed data from the Human Connectome project in order to see what the signal distributions that you have there really are. And so we try to determine the percentage, or let's say determine densities of SNR for the different shells for minimally processed data. And what we see here is that a high percentage, so for the shell with the largest p-value, 90% of the observations have an SNR smaller than 4. And 4 is for the shell distribution somehow the border where you really have large differences between expected value and theoretical signal. So where you have to take bias from coming from the data distribution into account when modeling. Okay, if you move to pre-processed data, and pre-processing means you apply a correction for magnetic field artifacts, for eddy currents, motion effects, which in principle are interpolations between neighboring points. This increases correlation and reduces variance and goes away from the shell distribution. So what you have afterwards is closer to a Gaussian due to averaging. And unfortunately, it does not affect the bias that you have in unprocessed data. And so the expected sigma depends on the scale parameter sigma of the minimally processed data. So that's something that you really need in the analysis. Okay, so let's go back to smoothing. What's different here, instead of 3D, you now have a location in 3D plus a location on the sphere corresponding to the direction. And this leads to a smoothing algorithm that employs different location weights here, and also employs a statistic dependency that incorporates information from different shells. Okay, what we get out of this is, again, the data from Leipzig, which has 4 replications of the experiment. This is the originally estimated color-coded FA map. This is the color-coded FA map that you get from using this smoothing procedure. And what you have here are for the unsmooth data and for the smooth data, the bias that comes from using a regression model instead of using the correct signal distribution. Also looking at the bias introduced. Okay, at last, quantitative anatomical MRE. What we have here is a situation where in an experiment you observe a sequence of images under different conditions, usually proton density, magnetic transfer, T1 weighted images with different TEs. They are related by a physical model, depending on different parameters, flipping, echo time, repetition time. So you have your observations, you have a model, you get parameter maps. And for high resolution, these parameter maps, they are quite noisy. What I've done here is applied the patch-based algorithm in a vectorized form, and this very well recovers underlying anatomical structure. Okay, let's sum up. I've introduced the structural adaptive smoothing concept that works in 1D, 2D, 3D, can be generalized to more complicated situations. Generalizations include patch-based variants for locally smooth images. I've shown that we can handle problems in high resolution MRA. And the last step, I would also like to mention our collaborators. My main collaborator is Carsten Tabelow from our institute. Henning Voss, Nikolaus Weizkopf, Joerg Polzehl, Martina Callahan are all MR physicists in different institutions. Lars Rototto, he was here for the last workshop. He is working in numerics, moving to deep learning in a moment. Remco Deutz is a differential geometer in Eindhoven. Okay, these are references, and there also is software, so usually all these algorithms are implemented as R packages, and some of them also as parts of toolboxes for the statistical parametric mapping system that's maintained at the Weierstraß-Institut for Neuroimaging in London. Okay, thank you for
Maybe we still have some time for questions, if you don't mind. So, if I understood correctly, you have kind of a priori assumptions, piecewise constant, piecewise polynomial.
Mm-hmm.
Whereas on the other hand, in this variational context, you usually look for a function space quantity which could be a priori infinite dimensional, but then sometimes we can do some analysis saying, okay, if you use this or that filter, the preference will be given to piecewise constant images. So, what kind of generalizations do you see here? You started out with Rn, piecewise constant, piecewise polynomial, and gave us some other examples here. So, what are the limitations in this respect?
Let's say limitation is that it really works if you have a parametric assumption that is valid inside some homogeneity region. The more complex the parametric assumption is, the less power you have in order to detect discontinuities. The large advantage of the procedure is that it's except that you need to know what your design space is and what the probability distribution or the class of probability distribution of your data is. It's data independent. It doesn't depend on the actual data set. So you don't have the problem of choosing a regularization parameter depending on.
Yeah, I'm not so sure because many things go in here which one has to see. But this would be my second question. So, I mean, so we did this TV opt thing where we tried to have, as I sometimes call it, a monolithic approach, where I would say I have a bilateral optimization problem. If you ask me what I give you back, I would say give an optimal weight for the filter according to this and that structure. But here I see a couple of steps. And what is there a kind of overall theoretical answer that the achieved weights have this or that property, or the reconstructions have this or that property?
Let's say the only answers, or the best answers that we have currently are the ones from the dissertation of Saskia Becker. And,
Just the one with this so this info
okay, so that's this type. It says if the model is correct and is correct globally, so we have only one region, then you can say exactly how, due to the choice of the parameter lambda, how the procedure behaves. You get similar results on a local homogeneity if you exclude certain regions around the discontinuities. You have a separation property that depends on the class of distributions through this parameter kappa. And she has also some error bounds under model specification, but they depend on an additional ingredient in the algorithm that we usually don't use because it's simply deteriorates results of that.
Maybe one last question. You gave us this comparison of different methods, and you gave us the P's and R's, I think it was.
Yeah.
So what about the run times of the methods?
Let's say for these 2D images, the runtime for non-local means was the fastest. I don't know the runtime for total variation. For adaptive weight smoothing, it's a few seconds on this computer. For the patch-based methods, it depends on patch size. So the patch size is a factor.
Of course, I mean the methods may have different levels of sophistication, implementation, or not.
But still, for let's say for the 3D examples, these were cubes of about 200 times 200 times 80 voxel, and even for a patch size of 5 times 5 times 5, I was running this on this computer yesterday in about an hour.
Also some question, maybe one which is related. So these weights, they live in image space times image space, at least for the non-patch based method?
No, the weights, they live in design space times design space. They always compare the situations in one point in design space with another point in design space.
Okay, the dimension of the design space is
The dimension of the design space in, for instance, in orientation space, diffusion and Mauer imaging is 5.
Okay, then another question. So this property that you have that becomes stationary if the distribution is indeed piecewise constant, does this extend to piecewise polynomial or not general?
Only by, let's say, this piecewise polynomial model construction, which transfers everything back to piecewise constant in the parameter space. The patch-based methods, they handle these things a little bit different because they allow for local gradients.
Another question, so is there any hope can you include somehow the forward operator to use, for instance, subsampling in R? So, for instance, for the weights, the part where you compare the signal value, one could maybe think of including first transforming the signal to Fourier space and then
Let's say
measuring the
in a moment I wouldn't know how to incorporate some linear or nonlinear operator because it's destroys the neighborhood structure. The question is, you always have to say, so it's a scale-space method, and you have to say which observations or which points in design space are close to each other and which are not.
Page 14, you have some experiments with C11. Yes. So,
let me go to a little bit more.
yes, whichever. In this kind of experiments, you don't assume you know the noise, you know details of what kind of noise, the spreads of noise. If you know everything of those, you can choose a specific method to deal with that particular case. But if you don't know this, so you have to use a more generic approach to do it. Right?
So usually my answer would be you have to look at the experiment that generates the data.
All right. So suppose you apply your method to the original image, pretending that you don't know the noise level on the original.
I would have to
what is the PS and R coming out of that?
It depends.
Yes. I mean,
so
this is the system limitation.
Yeah.
That means even for the clean image, you won't get 100%.
Let me go here. So I also have the
yes,
case
if you get
sigma,
so see what you get.
Which is probably less than the noise level which is in the image itself. And I see it.
It will come up with a number anyway. So, what is the number?
Let's say I see it when I use our robust method in order to estimate the noise level on the original image.
Yes, but
these images. And
you assume you don't know whether this is the original, though, even it's whether it's contaminated by something or not. You don't know. Then you just apply that and see whether there's still an error, quite big an error or something.
Let's say what you get is a situation that you get an estimate of your sigma by the robust method. This would be in a range of 0.01 to 0.02.
Can you get that accurate?
Depending on the assumption that you have a certain correlation structure.
All right.
The correlation structure comes in at that point, which makes things a bit difficult. And what we observe here for, let's say, in the first column, is that the adaptive weights recovers a little bit of the noise that I have added in the first and second step. And then it deteriorates in the sense that it starts putting small steps into the reconstruction.
Oh, okay.
And this is much less prominent with the patch-based methods. There I don't observe these things. So usually what we also tried was using these methods on really good MR data. So structural MR data where signal to noise is low. And in fact, we don't see a difference between reconstruction and the image we started with.
Okay.
will ask afterwards.
Okay, are there further questions? If not, then I would like to thank Mr. Polzehl once again. Thank you very much.